Exercise 5H, Modeling. Today we are learning about solving application problems involving both exponentials and logarithms. What you need to be able to do is break down worded problems into equations, draw a flowchart or some other way to be able to know how to solve the application question, find the unknown, and then write a worded answer. So I always start off with, where would we find exponentials in real life? Because obviously this kind of maths, we want to be able to apply it to something that's actually going on in the real world. Well, the most obvious answer that's happening, we're all right now, but maybe in the last year or two, is COVID. So first we started with one case, and then two cases, and then 4, 8, and it slowly grew up until it was thousands of cases. So that's what we would call exponential growth. So we started off quite slowly, and then it just kept going up. Now, of course, this isn't a model that lasts all the time, because at the moment it's a little bit more stable, but for a certain time, it was at exponential growth. Another example is something like population growth. So you might have one person who would then, you would have two people that comes from there, or that they might bring two people along with them. And then if these people bring another two people along with them, you can see that very slowly it starts to grow quickly. Another one might just be temperature of something. So for example, if you've got a hot cup of coffee, what we want to do, what might happen to that cup is that it's going to cool down quite quickly, and then it's going to get to a point where that temperature is going to balance out. So it might hit the temperature of the room, and then there's a point where it won't be cooling down anymore. So these are just different types of examples of where we could find exponentials in real life. And so that's what we're going to start looking at today. Example 22. Manoj pours himself a mug of coffee and gets distracted by a phone call before he can drink the coffee. The temperature of the cooling mug of the coffee is given by this particular equation, where T, capital T, is the temperature and little t is time, minutes after it was initially poured into the mug. What was its initial temperature when it was first poured? So the word initial means at the start, and that would of course be when the time is 0. So the way to be able to find that is we would just substitute in little t as 0. So that would be 20 plus 75e to the power of 0.062 times 0. Now all of this is going to be 0, and e to the power of 0 is just 1. So we'll have 20 plus 75, so that would be 95. And of course, because it's an application, we want to make sure that our units are correct. So at the beginning, the initial temperature of the coffee was 95 degrees. So part B then says, to what temperature will the coffee cool if left unattended? So the idea is that over time, it's going to hit a particular temperature that it's going to remain at. This is what we would call our asymptote. So if we want to try and think of this equation, what would this cup of coffee end up being? Well, it's going to start off up here at 95 degrees, and it's going to continue cooling until we hit that asymptote. And we can see from that equation that is going to be 20. So our asymptote is at y is equal to 20. So over time, it'll cool down to 20 degrees. Part C, how long does it take for the coffee to reach its temperature of 65 degrees? Give your answer correct to 2 decimal places. So the fact that it says correct to 2 decimal places indicates that at some point we will need to use our calculator. So now what we want is capital T to equal 65, and our question of how long indicates that we don't know what little t is going to equal. So all we have to do at this point is substitute in, and then we will work it out by hand for as far as we can get, and then at some point we're going to have to use the CAS calculator. So capital T, 65, is equal to 20 plus 75e to the power of negative 0.062 little t. That's what we don't know. The first thing I can do is I can take the 20 over, so that will give me 45, and then I can divide by 75. So that would be 75 is equal to e negative 0.062t. Then I can take the e over by taking log e of both sides. So I'll continue over here. That will be log e 45 on 75, and that is equal to negative 0.062t. And then, of course, to get t by itself, we can divide both sides by that value. So that will be negative 1 on 0.062 log e, and 45 on 75, we can simplify that down to 3 on 5 as well. Now, because it specifically said correct to 2 decimal places, we can go ahead and type that into our CAS calculator, in which case we'll get 8.24 minutes as our answer. Part D. Manoj returns to the coffee when it has reached 65 degrees and decides to reheat the coffee in the microwave. The temperature of the coffee in this warming stage, I think that's meant to say warming stage, is this particular equation. We've got two unknowns there. Given that the temperature of the reheated coffee cannot, and I think that's meant to say exceed 85 degrees, and that's meant to say calculate, not calcite, the value of A and B. So we have two unknowns and we have a bunch of equations there. So the first thing that we know is that Manoj returns to the coffee when it has reached 65 degrees. So what time was that? Well, that was at 8.24 minutes. So that's when he has returned to the coffee, and at that time the temperature was 65 degrees. We can think of this like a hybrid equation. So we've got our coffee which has cooled down, and now we're going to reheat it up. So it's going to go like that, like an exponential that has had a reflection in the y-axis. And at this point is going to be shared between both graphs, and that's this coordinate here, the 8.24 and 65. So I'll just write that out as a coordinate. So that's the first thing that we know. The next thing that we know is that the temperature of the reheated coffee cannot exceed 85 degrees. So that means there's going to be a point at which it cannot get any higher than that. And most likely it's not going to actually reach 85 degrees, it's just going to get very close to that. And that there would be the definition of our asymptote. So we can see that our asymptote is going to be at 85. And just looking at our equation here, this value A is going to be our asymptote. So in this case, we found our first value, A is equal to 85. And in order to find B, what we can now do is substitute this coordinate in and solve for B. So I might just move this to the side here. And now we can go ahead and sub in that coordinate in order to find B. So 65 is equal to 85 plus B is our unknown, and in fact the 8.24 should be where the T is. So it'll look like that. Now we're going to go ahead and rearrange for B. So the first thing is I'm going to take the 85 over to this side. That means I'll have negative 20 is equal to B, E, and that value, when we put that into the calculator, we will get 0.412. And then in order to take this over, remember this is just a number. So we can actually take that over by dividing both sides by that number. So B is equal to negative 20 on E to the power of negative 0.412. Now at this stage, what we can do is put that straight into our CAS and we can work out what our value is going to be. So when you put it into your CAS, you'll get B is equal to negative 30.20. And so we can now say that we've found the values of A and B. It doesn't say find the equation, it just asks us for A and B. So then this will be appropriate for your answer. Part E then says sketch a graph showing the temperature of the coffee during its cooling and warming stage. So we want both of our functions, so just like a hybrid function. Because it's an application, what we're going to do is just draw up the first quadrant. This axis here is going to be little t for time, and this will be capital T for the temperature. Now for our first graph, if you look back over the parts, we found out that the initial temperature was 95 degrees. And then it cooled down all the way to 65 degrees. And that happened at 8.24. So it's going to cool down to this point here. And from there, what we did was we reheated it. However, it could not exceed the temperature of 85. So if 85 is over here, that's going to be our asymptote, and our equation would look like this. So there you go, that's what your hybrid function should look like. Next example, example 23. A biologist conducts an experiment to determine conditions that affect the growth of bacteria. Her initial experiment finds the growth of the population of bacteria is modeled by the rule n is equal to 22 times 2 to the power of t, where capital N is the number of bacteria after t days. First question, how long will it take for the number of bacteria to reach 2816? Well, this value here is n, and when it's asking us how long, it's asking for the time. So this is just going to be a simple substitution into that particular equation. So we'll have 2816 is equal to 22 times 2 to the power of t. We can rearrange by firstly dividing by 22, and then taking the base over by taking the log 2 of this side. And then when we put that into our CAS calculator, what we'll find is that that is equal to 7. So our answer will be 7 days. Part B, what will happen to the number of bacteria in the long term according to this model? So what we mean by the long term is that as t approaches infinity. So what you need to think about is what is happening as t continues to grow. The best way to think about this is let's draw what this situation is going to look like. It's an exponential function with no reflections, so it is going to look like this. So what we can see is that as t continues, this exponential function will continue to rise. It doesn't approach an asymptote. So as in the long run, as in when time approaches infinity, then the number of bacteria will likewise approach infinity. It will keep growing exponentially. And we can also say that that's going to happen indefinitely because there is no asymptote. It'll just continue that growth trend. Part C, the biologist changes the conditions of the growth of the population of bacteria, and it's going to be modeled by that particular rule there. Firstly, show that in both of her experiments, the biologist used the same initial number of bacteria. So our keyword there is initial. That means when time is equal to 0. Remember, when we use the word show, it means that we need to start at a particular point and then get to our answer. So we can't use our answer in our question. Luckily, they haven't actually given us an answer in this case. So what we have to do is we just have to use both experiments and find out what it is that we started with. So this will be experiment number 1. Experiment 1 was our equation 22 times 2 to the power of t. Because it's initial, we're just going to make it 2 to the power of 0. 2 to the power of 0 is 1, so that will just be 22. For experiment 2, we're going to do the same thing where we're going to make t is equal to 0. So that's n equals 66 on 1 plus 2 e to the power of negative 0.2 times 0. Now, negative 0.2 times 0 is just 0, and e to the power of 0 is 1. So that'll be 66 divided by 3, because 1 plus 2 is 3, and then 66 divided by 3 is 22. So as we can see, experiment 1 is equal to experiment 2 when t is equal to 0, and very specifically, our initial number is 22. Part 2 says what will happen to the number of bacteria in the long term. So again, as t approaches infinity, according to her second model. So the easiest way to think about this, you can graph this. If you have a CAS calculator on hand, you can graph it. However, this particular function, we don't really know what it looks like. So what we're going to do, obviously we can't substitute in the term infinity, but what we're going to do is we're going to sub in a very, very large number, and you can practice this on your CAS calculator. So if we were to write out our equation, 1 plus 2e, negative 0.2 times, and you can practice this by putting in a large number. I'm just going to put in 99999, put in as many 9s as you like, and see what happens there. Now, just in terms of this number, let's just focus on this particular number. So if I have 2e to a very large number, and remember it's negative, what that means, the negative means that I can take it to the bottom. So that's 2 divided by e to a very large number. Now give that a shot with your own CAS. Put 2 divided by e to the power of 99999 and see what happens. Any number divided by a very large number is going to get closer and closer to 0. And you will see that as you practice that on your test. So if you have 1 divided by 2, then compared to 1 divided by 100 or 1,000 or a million, that number is going to get closer and closer to 0. So what we can say is that as t approaches infinity for this particular term, this term here, so 2e to the power of negative 0.2t, that is going to approach 0. So essentially, this particular term is going to get closer and closer to 0. Now, if that term is basically 0, what do we have left over? Well, all that's going to be left over is 66 on 1, which is 66. So what does that tell us? It tells us as time gets closer and closer to infinity, as in the long term, then our number of bacteria is going to get closer and closer to 66. Next example, example 24. Carbon-14 dating measures the amount of radioactive carbon-14 in fossils. This can be modeled by this particular relationship, where Q is the amount in milligrams of carbon-14 currently present in the fossil of an organism, and T is the time in years since the organism's death, and Q0 is the initial amount in milligrams of the carbon-14 present. Part A. A fossil shell initially has 150 milligrams of carbon-14 present. How much carbon-14 will be present after 2,000 years? Give your answer correct to 3 decimal places. So we've got a lot of information here. What we know is that this relationship is between Q and T, and Q0 is going to be representing my initial amount. For part A, they've told us that initially there is 150 milligrams of carbon-14 present. So let's try and write that out in terms of our variables. When T is equal to 0, Q is equal to 150. Now, usually we would need to substitute this in and solve for A, which would normally be my variable that's outside of E. But in this case, they've actually specifically told me that Q0 is the initial amount. So immediately I can find out that Q0 is going to be 150. Then it asks us how much carbon-14 will be present after 2,000 years. So how much carbon-14 means I don't know what Q is, but I do know that T is going to be 2,000. And then it also says give your answer correct to 3 decimal places, which implies that at some point we're going to need to use our calculator. So let's set up our equation so far. So it's 150e to the power of this very small number. And now we're going to sub in the information that we know. So we are finding out that we want, that's actually the wrong place. We actually don't know what Q is. However, we do know that we want it to be after 2,000 years. Now, at this point, these are all numbers, so all we can do it here, we can't rearrange or anything, we can just put that straight into our CAS calculator. So we get 117.054 milligrams. Part B, find the number of years. So again, this time what we're doing is we don't know what T is. It will take for the carbon-14 in the shell to be halved. Give your answer correct to the nearest year. So initially I had 150, and now what we want is for it to be half of that. So that means I want Q to be 75. So again, all I have to do is substitute these values into my equation. So 75 is going to equal 150e, our very small number, and this time I don't know what T is. Now what you can do is you can divide by 150, and then take the log base e to the other side. Or, of course, you can just type that straight into your calculator and solve for T. When you do that, you will get that T will be 5,589.9, and it specifically says answer correct to the nearest year. So we're going to round up to 5,590 years. Part C. Suppose the amount of carbon-14 in the shell is Q0 on N. So that's the amount, which means that's going to be Q. Find an equation relating N to T. So our initial equation was relating Q to T. Now what we want is for it to relate N to T. Then, so that's the first thing that we have to do. Then it says, hence find how long it will be. So how long? That's T equals question mark. Before the amount of carbon-14 in the fossil shell is Q0 on 10. give your answer to the nearest year. So what we want again is an equation between n and t, not q and t like we've had previously. So I'm just going to quickly write our equation that we normally have. And we kind of want to get rid of this q and somehow replace it with an n. Well, that's really convenient because it's telling me that the amount that I have can be represented by q0 on n. And I know what q0 is, that's 150 on n. So what I can do is I can substitute that into my equation, and you can see already how I've gotten rid of the q and instead I've introduced my variable n. Now, because I want the equation to be relating the two variables, we just want to rearrange it in a nice format so that I can have n equals and then something to do with t. So the first thing is if I divide both sides up by 150, that is going to cancel out. And then I'll have 1 on n is equal to e. What we can do in this case is take the n to the other side, and I can also take, therefore, this to the other side. However, this has a negative number, so if I just write it on the side here, that's x, for example, to the power of -1, which is the same as 1 on x. So that's already on the bottom, so if I want to take it to the top, it's no longer a negative power. It will no longer be a negative power. So I'm going to flip both sides over. That's going to be n is equal to, and if I flip this to the top, it will no longer be negative. So from there, I can see that I've got my equation in terms of n and t. So that's part one. So q0 on 10, if you relate it back to what they initially said about the amount, they initially said that the amount is q0 on n. That means n must be equal to 10, and I can substitute that directly into my equation and solve for t. If I do that, I get t is equal to 18569 years. And that's the end of this modelling chapter. Take care.